So, have you ever really stopped and wondered how your computer actually thinks? We're about to peel back the curtain and uncover the secret language that powers literally everything you do on your devices.
I mean, think about it. You click a single icon, and this entire complex universe of a program just springs to life. How in the world does a machine go from that one little input to something so huge? It feels like magic, doesn't it? But what's really going on is actually way more elegant. And here's the secret, the real kicker. Your computer isn't some kind of super genius. Not at all. It's just an incredibly fast, and I mean insanely fast, follower of really, really simple instructions. We're talking billions of them every single second.
Okay, so let's start at square one. What are these simple commands? What is the secret language that makes our entire digital world possible? A computer instruction is the absolute most basic command there is. It's one single, tiny task that the CPU, the brain of the computer, can understand and carry out. You can just think of it as a single word in the CPU's own native language. And don't get it twisted, these instructions are absolutely everything. They're the fundamental building blocks for all software. Without them, a computer is just a really expensive paperweight. I mean, they control every calculation, every time you hit a key, every single pixel you see on your screen. So if an instruction is like a word, it must have some kind of structure, right? A sort of grammar. So let's crack one open and see what it's made of. Okay, the first part is called the opcode, which stands for operation code. The easiest way to think about it is as the verb of the instruction. It's the action word. It's what tells the CPU what to do, like add or load or store. And if the opcode is the verb, then you gotta have a noun. That's the operand. It's the thing that the action is happening to. So if the opcode says add, the operands are the numbers you're gonna add. If it says load, the operand is the place in memory you're loading from. Verb, meet noun. It's that simple. Now, a CPU needs a place to get its work done, right? When it's in the middle of a big calculation, where does it keep the numbers it's working on? It can't just keep reaching all the way out to the main memory every single time. That would be way, way too slow. It needs a little workspace right there at its fingertips. And that's exactly what registers are. They're these little pockets of super high-speed storage located right inside the CPU itself. And this analogy is perfect. If your main memory, your RAM, is the big pantry down the hall, registers are the tiny countertop right next to the stove. They only hold the ingredients or the data that you need right now. These registers are just essential for efficiency. They hold the data for the current math problem, the instruction the CPU is working on at this very moment, and they even keep track of the address of the next instruction it needs to go grab. They're basically the CPU's short-term memory, making everything run buttery smooth. So we've got our CPU, we've got our memory, and we've got these super fast registers. But how do they all talk to each other? How does data get from that pantry to the countertop? Well, they need an information highway. Think about it like this. Inside your computer, all these different parts need to send and receive information constantly. But you can't have them all shouting at once. That would be total chaos. You need an orderly system for everyone to communicate. And that system is called the common bus. It's basically a shared set of wires, a data highway that connects all the key components together. And here's the rule. Only one component can send data on the bus at any given moment. This prevents chaos and makes sure information gets where it needs to go, one transfer at a time. Of course, as computers got more and more powerful, this system had to evolve. Early designs used a single bus, which was simple and cheap, but it created a traffic jam, a bottleneck. So modern, high-performance processors often use multiple buses, which is like adding more lanes to the highway. It allows different parts to talk at the same time, which, you guessed it, means a huge boost in speed, but at the cost of more complexity and money. Okay, so we've met all the players on the field. We've got the instructions, we've got the CPU's workspace and the registers, and we have the information highway, the bus that connects them all. Now it's time for the main event. Let's put it all together and see the engine of the computer in action. You see, the real heart of the CPU isn't one big, complicated thing. It's a constant repeating cycle, a simple three-step dance that it performs relentlessly, over and over, at a speed that is almost impossible for us to even comprehend. And that three-step dance is the famous instruction cycle, and this brilliantly illustrates just how simple it is at its core. First, you've got fetch. The CPU reaches out and grabs the next instruction from memory. Then comes decode. It looks at the instruction and figures out exactly what it's being told to do. And finally, execute. The CPU gets to work and performs that action. Fetch, decode, execute, over and over. Now, what's really amazing is that modern CPUs don't even do this one by one anymore. They use a trick called pipelining. Imagine an assembly line. While one instruction is executing, the next one is being decoded, and the one after that is being fetched, all at the same time. It's how they get so much done so incredibly fast. And that's it. That's the whole shebang. Fetch, decode, execute. This is the heartbeat of your computer. Sending an email, playing a game, watching this explainer right now, it's all just millions and billions of these simple little cycles happening one after another. This is the fundamental rhythm of all modern computing. And that leaves us with a pretty fascinating question to chew on. If every piece of complex software we've ever created, from a simple calculator to the most advanced AI, is ultimately just a massive sequence of these incredibly simple logical steps, what does that imply? It kind of suggests that maybe, just maybe, even the most complex intelligence is really just simplicity scaled up to an unbelievable level. Now, that's something to think about.